Good morning. It's a beautiful spring morning in Decagon Devices here in Pullman, Washington. I'm pleased to be here. My name is Michael Hecht. I'm the Assistant Director of MIT's Haystack Observatory, but until recently, I was a Senior Research Scientist at Caltech's Jet Propulsion Laboratory, which is the NASA installation that's responsible for exploring the solar system. It's 3 weeks before the 5th anniversary of the landing of the Phoenix mission on the northern plane of Mars. And I was fortunate enough to be the principal investigator for an instrument suite on that mission that went by the acronym MECO, the Microscopy, Electrochemistry, and Conductivity Analyzer. MECO was put together by a small group of partners, one of whom was Decagon Devices, and was a very successful instrument suite and made a significant contribution to our understanding of the red planet. When you walk through the door here at Decagon Devices, you're greeted with a large painted sign on the wall that reminds you to think like a scientist, to work like a farmer, to dream like a child. And it struck me when I first saw that those are exactly the attributes needed to do science on another planet. And I can also say from my experience with my friends and colleagues here that this is an institution that walks that walk with a lot of enthusiasm. So I'll get right to it and tell you a little bit about the instrument that was developed here, the Thermal and Electrical Conductivity Probe, the TECP, and the MECO instrument suite it was part of, and the Phoenix mission that, in turn, that was part of. You can see in this first slide the colorful logo of the Phoenix mission that it landed in 2000, that was launched in 2007, landed in 2008, and our MECO payload package covered with real dirt from Mars, and that's a site that I can look at. I don't care how many times I look at it, always gives me pause just to think about something you built and touched with your own hands, covered with soil from another planet. So let's go ahead, and I'll tell you a little bit about the background of the mission. The Phoenix mission was named not after the city, because in fact it was run out of Tucson, Arizona, the University of Arizona. It was named after the mythical bird and the fact that so much of the mission, so much of the payload was taken from previous missions that had been canceled, or in the case of Mars Polar Lander, that had failed and crashed. So those instruments were rebuilt and repurposed for a mission that for the first time was going to go to a place on Mars where water ice could be found. I've put on this slide a quote from Robert Frost, who's equating ice with hatred and fire with desire, and talking about how the world will end. And it ends to say that for destruction, ice is also great and would suffice, is a good description of the planet Mars. It has died in ice. It's not a ice water-free planet. What it may be lacking and is likely lacking is liquid water. But there's lots of ice on the planet. You can see that through a telescope in your backyard at the right time of year. As you see on the left-hand side, there's a large polar cap made of water ice. And on the right-hand side, you see a more revealing image map that was taken with a spectrometer in orbit looking for neutrons coming out of the planet. And all that you see in green and blue and pink in the middle are different degrees of water ice that are measured just below the surface, a couple of inches below the surface. So we know that Mars has polar caps with a lot of water ice. It has a region of permafrost like the Arctic or Siberia on Earth. And then it has a large, dry equatorial region where the temperatures might occasionally get warm enough for liquid water, but there's just no water to be found. So while NASA has been theming the Mars program for some years as follow the water, that's typically meant look for signs of ancient water in the equator region. And what we did for the first time was to go where, in fact, there's water, at least H2O, today. Okay, so the big question is whether there is liquid water on the planet. There have been any number of reports of hints of such water, such as these recurring slope lineae that were seen with the Mars Reconnaissance Orbiter camera. And these certainly look like signs of some kind of streams that are seasonal. They darken and lighten with the season. The climate conditions where they're found suggest these would have to be very briny. They couldn't be fresh water or they would freeze. But there are hints. There may be other explanation, but there are hints of liquid. So what we can maybe conclude, to stay with the poetry theme a little bit, is the words of Samuel Coleridge: water, water everywhere, but not a drop to drink. Briny water or ice is what we expect to find on Mars. So the Phoenix mission. This is an artist's conception. There was nobody at this particular vantage point to take a picture. But you see the spacecraft sitting in a terrain that looks sort of lumpy. From the air, this would look like polygons, much as you see in frozen regions on Earth that are due to cracking, to systematic cracking of the ice just under the dusty surface. And that surface layer, again, as on Earth, goes maybe a few inches deep, and is there because during the day, that thin layer will heat up and will drive out any water, but that thin layer thermally protects the ice underneath and keeps it stable over time. So the mission was designed, as you can see, with a robotic arm to be able to bring samples of that dirt up to different instruments. It does not have wheels. Much is the same. If we were to rove around this terrain, we would be unlikely to find anything particularly different. So for a low-cost mission, what we dispensed with were the wheels. There were two significant soil payloads on the mission. One was MECO, which I mentioned. The other was TEGA, the Thermal and Evolved Gas Analyzer, which I won't speak about today. There is also, of course, a camera, the Surface Stereo Imager, a second camera on the robotic arm, meteorological instruments on a mast, including a LiDAR, which is a laser radar system for looking at clouds and other types of aerosols in the atmosphere. So to narrow in again, let's talk about the MECO instrument, the Mars, what was originally called the Mars Environmental Compatibility Assessment when it was first conceived as a mission to explore potential hazards to humans going to Mars, and what was called, when it was repurposed for this mission, the Microscopy, Electrochemistry, and Conductivity Analyzer. So the microscopy part is an optical microscope and a sample wheel on the upper left, as well as an atomic force microscope that was put together by three companies. Transfer Engineering built the mechanisms, University of Arizona built the optical microscope, and a Swiss consortium led by the University of Neuchâtel built the atomic force microscope. On the right and on the bottom, you see the wet chemistry laboratories, 4 identical chemistry cells. The chemical beaker was built by what was originally Orion Research, and at the time of the mission was part of Thermo Fisher. And the Starsus Research Corporation built all the mechanisms you see on top for stirring and adding dirt and unfreezing the water and maintaining thermal control and adding reagents. And again, I will touch on that briefly today, but I mostly want to talk about the instrument in the lower right, the TECP, which was made here at Decagon Devices. And that's for actually inserting in the soil and measuring properties of the soil related to water in all 3 phases, in the vapor phase, in the liquid phase, and in the solid phase as ice. Okay, so why? Why are we interested in studying dirt? Why do we go all the way to Mars to study dirt? Well, first of all, if you want to understand Mars, soil plays a central role in the way the planet works. Nearly every process happening on the surface, and I don't care whether that's a potential microbe or human beings that are planning to walk around on it, or whether it has to do with scouring of rocks and aging of rocks, whether it has to do with modifying how the sunlight is absorbed and providing feedback to climate cycles. All of these things are due to the characteristics of the soil, because that's what's actually exposed. In addition, what we call the boundary layer, the bottom of the atmosphere, the part that we all live in, that we experience, on Mars is dominated by dust in the air. That's the major, that would be the weather report on Mars. You know, what's the dust doing today? Is it blowing around in dust devils? Is it quiet? Is there a dust storm brewing? And all of that affects how light gets through the atmosphere, which affects everything from whether we can get power into our solar panels on our experiment to how hot the planet gets in the summer and how cold it gets in the winter. It turns out over long enough time, these particles are a window into the geological processes. They all come from somewhere. They come from rocks. Each particle you look at was once a rock. And understanding how it went from being a rock to being a tiny grain of sand is a very exciting proposition and a window into how geology works on another planet. And finally, the fact that this dust and soil is a significant hazard to humans when we go to explore Mars. And while this may sound a little odd, if you had an opportunity to ask an Apollo astronaut what the most hazardous part of the journey to the moon was, they'll tell you it was the dust that was abrasive, that stuck to everything, that got in everywhere, that literally wore holes in their suits. So we anticipate the same issues to be possibly the case on Mars. So that's why we study it. I always like to put up this picture of the launch of the beautifully decorated rocket with the teal blue and the Phoenix logo that launched from Cape Kennedy back in August of 2007, because it's simply humbling. When my team and I work on an instrument that sits on a computer table that's very small that you can all gather around, and we put instruments like the little TECP that's that big in it, and then bolt it onto a lander that is maybe the size of a kitchen table. It's somehow very again, humbling to see this 150-foot rocket that has been built to take it on its journey to Mars. And what an enormous enterprise, with how many thousands of people have to come together as this enormous village that allows us to do science on another planet. And quite simply, it's awe-inspiring to see this second sun rising out of the sands of Cape Canaveral over the ocean. So we launched. I like to show this slide for no particular reason except as evidence of the agony and the ecstasy of these things. These were events in and around the landing, both the sheer joy of taking that first step onto a new planet, and the extreme worry about all the possible things that can go wrong in those moments of terror before the landing. Okay, so where do we go? You see in the upper left, in the blue area, where it says Phoenix. The previous landers on Mars are marked elsewhere on this map. Phoenix has gone, as you can see, much farther north than anyone else has gone before. The blue doesn't indicate on this map ice or water. It indicates a very low elevation. This is an elevation map, and this shows you the whole map of the planet Mars, and you see immediately that there's what's sometimes called a dichotomy. There's a very low, what might have once been a sea or an ocean, covering the northern plains of Mars, whereas the south is this very old, very high, and I say high, literally a few kilometers higher than those northern plains. So we're going to the northern lowlands, very far north, where the previous map I showed you at the beginning indicated that just below the surface we ought to find ice. This is another picture I always show just because it is awe-inspiring. When we look at Mars from orbit, from the skies, you know, you always might dream or imagine you see something moving. And here, indeed, we did capture something moving, and it was the Phoenix spacecraft landing. And if you look close at what's going on in the part that's enhanced in the lower left corner, you can actually see the cords in the parachute lowering Phoenix to the ground just off to the right of this Heimdall crater that you're looking at. It was an astonishing picture. We've done similar things since with the Curiosity mission, but this was the first time we had ever seen a spacecraft land on another planet. Also, with the quality of the cameras we have in orbit in Mars, we're able to see the lander itself on the ground. You can see what looks like an inverted Mickey Mouse head. You can see the lander itself from the two large circular solar panels, and an area where we've blown a very, very fine layer of dust off the surface with the landing jets that's somewhat darkened for 10 or 20 meters around the landing site. So zooming in more, this is the picture from the ground. So that same polygonal terrain you see now looks like this bumpy, lumpy Mars landscape. You see the robot arm we brought to dig soil, where it has its first scoopful of soil, and you're looking out over one of the solar panels. And this is, if you will, the Martian Tundra. If we take our little black and white camera, our little monochrome camera that's in the end of the robot arm, and stick the robot arm down and underneath, we could look below to see what damage our landing jets did. And astonishingly, we saw a big patch where that surface soil had been blown out, and we could directly see a big circle of ice immediately under the lander. So already we knew we were successful, that our understanding about what was underneath the soil was at least in part true, that there was indeed a sheet of ice. And just in the lower left, you can in fact see the TECP sticking out from the arm and just getting a little bit in the way of the camera view. The camera is mounted right on top of the TECP. Okay, so this was the next confirmation that white stuff we were looking at, which we literally were calling white stuff until we had a confirmation. This is the confirmation. It was in ice. It was actually ice and not, say, some kind of salts. And in the left-hand circle, you see some chunks of ice that had been dislodged by the robot arm scoop. And on the right-hand side, you see that after 2 sols, which are 2 Martian days, it's sublimated away, and therefore it's got to be ice. There's nothing else one would find on Mars that would be volatile at surface temperatures. So that was our proof. We found what we were looking for, and while there's lots to talk about on the mission and on MECO, let's talk about this TECP. You see here a good view of it on the robot arm scoop looking at you, and another one with it inserted into the ground, and you can see the shadow demonstrating how perfectly it's put in the ground. That wasn't easy to do. That took a lot of learning, but let me first tell you a little bit about what this instrument is. You see 4 needles here, each of which have a specific purpose, and one of them is an electrical ground. One of them, we can select which one is used as a heater. The one next to the heater is used to measure the temperature transfer from the heater to the next needle, and that's one of the ways, that's the way we measure thermal conductivity and heat capacity. Yet another one is used as the rest of the electrical contact at different frequencies to measure both permittivity and electrical conductivity. The conductivity tells you if there's actually any liquid films, any liquid briny films in the soil. We never saw those. And the permittivity tells you whether there's sort of unfrozen films of water where the molecules might be able to jiggle around. It's not actually icy, but it's not actually liquid. And the thermal measurements are sensitive to the presence of ice. So that's what all the needles do. You can see a little picture in the lower left of the circuit board that enables this. And the little circle on the side is a humidity sensor, so we can measure water in the vapor phase as well as the solid and the liquid. So that's the instrument. This was one of the many, many, many kinds of displays the robot arm people used as they learned, they literally had to learn on the surface of the planet how to insert these needles in the ground cleanly so they didn't move around and expand the holes or leave gaps. And the color coding is showing the elevation, because when they position the robot arm, they have to know exactly what height to put it at, not just the 2D picture. And every rock here has a name, mostly named after fairy tale characters, and so that we could talk about them. And there's a little point marked with a star close to the rock marked headless, which was our first insertion point of the TECP. And we went on then to study that insertion, trying it different ways with different amounts of pressure. You can see the holes left behind on the left. The one in the center of the panel was the cleanest of the different methods we tried. You can see the shadow of the TECP at the upper left of that picture. We actually used the permittivity measurements as an indication of whether we had a good clean insertion and good contact. So you can see the one on the top was the cleanest, and that involved a little more pressure than we had anticipated, and that's the method we used subsequently. Okay, if you want to know more about the results, I would point you to the Journal of Geophysical Research. The initial results, which were really the most exciting results that I will summarize from the TECP, and the authors on that were Aaron Zent, who was the principal scientist in my team responsible for the TECP, myself, and Doug Kobos here at Decagon, who was the project manager and a great asset in terms of interpreting, modeling, and understanding the physical processes, the soil processes that the data represented. So I'll start with, in some sense, the most workmanlike of the measurements, the thermal and electrical conductivity. And I say that in the sense that we have many spacecraft now that have gone to Mars, measured many things on Mars, and to some extent you contribute to a body of knowledge and fill in the gaps. That's what we were after here. We've mapped what a property called thermal inertia from orbit, which is a combination of thermal conductivity and heat capacity that measures how quickly things heat up and cool down, because that's what you can in fact measure from orbit. And so what we were able to do is to go in, and on this picture with the little circles, and narrow down the values that had been measured from orbit into a much narrower range, first of all. And second of all, by being able to do what you couldn't do from orbit and separate the contributions of conductivity from heat capacity, we could actually say something about the soil and, for example, how densely it's packed within a certain model to explain these results. So we can then take this as what we call ground truth and feed it back to interpret the measurements all around the planet. So that was a very important measurement. Permittivity, in some ways, was the one we were most excited about when we started, because we had all the speculation about whether you might have any liquid films under any circumstances. The results we got were interesting. We found, first of all, in the upper left picture, a tremendous variation from insertion to insertion, just as a warning that there were some issues that we had to be careful of that had to do with how good a contact the needles were making. But in the bottom frame, when we adjusted all that and normalized it to a common starting point, we saw some very interesting things. We saw that after a certain point in the mission, when it was getting warmer out, at certain times of the day, at the nighttime in particular, we would see large variations in the permittivity. Now that certainly points to times when you might expect to be seeing liquid films. Nighttime, because you want to condense the water out of the atmosphere, is frost, but the warmer time of year when you don't want it to condense so cold that it can't possibly form a brine. And indeed, there are changes in permittivity there. We were a little puzzled when we did the models of this, because the changes were larger than we would expect, and we don't understand it yet. So I would say this is a work in progress. There's clearly something very interesting going on that we were looking for that's suggestive of liquid films, but we don't understand what it's telling us yet. The surprise here was the humidity measurement, which was almost an afterthought. We added that sensor, Decagon added that sensor for us with very little fuss halfway through the development of the project. And it turned out to be of tremendous importance in our understanding about, if you will, how Mars works. So you see in the upper right panel, there's a number of measurements taken by various instruments of the temperature, going from the nighttime to the daytime in the middle and back down to the nighttime. And you can see the temperatures go from, this I believe is in Kelvin, but go from, from minus 100 and some odd degrees in some cases to barely above the freezing point. Now, on top of that, you can see in the gray the humidity measurements from the TECP converted into a frost point. Because humidity and frost point are two ways of looking at the same thing. Frost point tells you at what temperature the water vapor starts falling out of the air. And you can see that the frost point tracks the temperature at night, almost but not quite perfectly, which is a way of saying simply that the amount of water vapor in the air is determined by how cold the ground is. When the ground gets cold, the water vapor comes out and it's not replenished fast enough. The ground controls the amount of water in the air, much as it does on Earth, but frankly, something we hadn't really realized in previous models of Mars. People had always thought about humidity being a property of the atmosphere, not a property of the ground. The interesting thing is what happens in the daytime, and that had everybody puzzled for some time, because it saturates at a certain amount of water in the air, a certain absolute amount of water, a certain number of molecules per square centimeter, equal to 1.8 Pascal in pressure. And why that number? What's special about that number? Is that just how much water there is in the air? And we finally sorted that out, and it was one of these discoveries that, once we understood it, was astonishingly simple. And it has to do with the fact that just a couple of centimeters below the surface is a sheet of ice that's more or less at a constant temperature. It's protected from the daily temperature variations, as you see in the lower right picture, by this layer of soil. So it's always around 215, 217 Kelvin this time of year. Now, that particular temperature ice has a certain vapor pressure, which is just about 1.8 Pascal. In other words, the daytime water vapor simply reflected the fact that the water was in equilibrium with the ice under that little blanket of soil, and nothing more. And it was telling us that it's the ground, again, that controls the water vapor in the atmosphere of Mars. Sounds obvious in hindsight. Nobody realized it until that experiment was done. So that was of tremendous value. And all that happens at night, essentially, is the top of the soil becomes colder than the ice. So that's the place the water goes. In the daytime, the top of the soil is warmer than the ice, so the water vapor just goes back and forth into the ice itself. That was a major, major finding. A related question has to do with where in the atmosphere the water is. How is it distributed? It's always been assumed in the past that that water vapor is well mixed over what's called a scale height, which is about 10 kilometers. And we've known since the days of Viking exactly how much, as a function of the latitude on the planet, as a function of the day of the year, how much water vapor is in that total column. What we haven't known is how it's distributed. Is it well mixed so that it's one pressure at the bottom and one at the top? We don't know. Is there a supply of water from the top? Is there a sink of water at the top? Again, how tall is in practice that height? And right away with the TECP measurement, we knew that our current understanding was wrong. It was much too high. What we measured was about 4 times higher than you'd expect from a well-mixed atmosphere, suggesting that most of that water vapor is probably near the ground. It turns out that some other suggestions of that had been published in the literature fairly recently, and it has an interesting implication. You know, what happens if most of the water vapor is in the lower 25% of the atmosphere, other than the fact that the density of water vapor is 4 times greater than we thought? Well, it turns out I've done some modeling that shows that the latitude range over which ice is stable, that permafrost is stable, goes from about 50 degrees, which everyone thought was the end of the ice sheet, down to about 40 degrees, which is much farther south than people thought. In fact, it suggests that the second Viking lander was sitting on an ice sheet as well. Now, it turns out recently there's been some very puzzling measurements, images that people have acquired that they didn't understand. These images have been of fresh craters, literally within, captured from cameras in orbit within a week of their formation. These are little things about the size of a meter across that immediately show ice just below the surface at latitudes where no one thought there could be ice before, all the way down to 40 degrees north latitude. So the TECP has stitched this whole picture together to say, we were wrong about the water vapor density on the surface, so we were wrong about the frost point, so we were wrong about how far from the North Pole this ice can be stable, and that's why we see ice at these latitudes. A major contribution. Okay, so how about the rest of the story? I've summarized again the important results. The humidity versus temperature gave us both a new understanding of how water is regulated in the atmosphere above the surface, that it's regulated by the ground, and it also gave us a new understanding of where ice below the surface is stable. The permittivity suggests something is going on suggestive of water, but we don't quite yet understand what that might be, but we can speculate that it has to do with frost and it has to do with brines. The next step is to improve the calibration on the humidity, to create a simulant so we can try to reproduce in the laboratory these permittivity measurements, and maybe to start developing the next generation of this instrument for a future opportunity. I wish I could tell you all these things were happening with a great frenzy of activity. And the reality is, as I've written here, the bad news is that right now, there's so much going on in the Mars business. Mars researchers are inundated with new projects, new opportunities, new missions, new data, and have very little time or money, for that matter, to look back in the detail deserved. And of course, I have to point out that the good news is that Mars researchers are inundated with new projects and new missions and new data to look at. So we will all catch up with this in time. This is a golden era in the history of Mars exploration. And once all that data is back on Earth, we can explain it and understand it at our leisure, and that's what we're doing. So let me tell you a little bit about some of the other elements of the MECO payload, and let's start with the wet chemistry laboratory. Wet chemistry is a new thing on Mars. In the past, people have used different kinds of techniques to look at the elements that make up the rocks and the soil of Mars. We first decided to do wet chemistry, which I should say is more or less like the chemistry many of you did in junior high school, where you take a beaker and you put an unknown in it and you use litmus paper or probes or add reagents, stir it around and learn about what that unknown is and then write a lab report. We've all done this. This hasn't been done on Mars. It's difficult to do on Mars. We originally undertook this approach because, as I mentioned, MECO was first designed to look for hazards to human exploration. And quite frankly, anything that's going to be hazardous or poisonous or chemically corrosive to a human needs to first be soluble. If it's not going to dissolve in water, in your breakfast cereal, in the linings of your lungs, or even on equipment, it's not going to hurt anything. So soluble chemistry, wet chemistry, specifically looks at all those species that come out when a sample's put in water. It's different from doing an elemental study of the whole sample. So I showed you quickly the cells we use to do this, and I don't have time to go into all of the challenges in actually getting, there is liquid water on Mars. We brought it there, and it wasn't easy. But I will show you the first thing we saw, which was the pH measurement, and you can see it rising from the level of the solution we started with to a slightly basic, neutral, slightly basic level as soon as we added the soil. Now, again, a lot of these things make a great deal of sense in hindsight. Right up until literally the month we landed on Mars, there were articles in the literature saying that Mars soil must be very acidic. So right away, when we saw this, there was amazement. My goodness, this isn't how it's supposed to look. Now, one of the ideas that I was developing and many of my colleagues were developing as we looked more and more at dirt is the idea that it is globally almost uniform on Mars, that what the dirt represents are samples of little tiny micro rocks from all over the planet, and that any kind of rock you see anywhere on the planet might be represented in any teaspoonful of soil. And so up here is a picture taken from one of the MER rovers that's actually an infrared picture that's been colored to represent the different mineralogies. And the minerals in blue are carbonates, which we found as well in our samples. And that's the reason the pH is near neutral. When you add carbonate to a solution, it buffers the pH at slightly basic or neutral, which is the case almost everywhere on Earth. That's why if you look at your tap water or a nearby lake, except in a few exotic places, you'll find pH around the same level we found on Mars, and for the same reason. The only difference being that most of the carbonate on Earth comes from life, from organisms, whereas as far as we know, on Mars, it comes from non-biological, abiological sources. So that was the first surprise from chemistry. We then went and measured a whole bunch of other species, cations and anions, magnesium, calcium, sodium, potassium for the cations. The anions were among the most interesting results. We had an indirect way to measure sulfate. We expected to find it, and we did. I mentioned the carbonate that we found. We expected to find halides, chloride. And that was where the big surprise of the entire mission, and I'd say a finding that has colored everything that's been done on the current Curiosity mission, we found that there was a tremendous amount of perchlorate, ClO4, rather than chloride, Cl-. Now this sounds like a trivial thing, and it turns out it's not. Perchlorate as compared to chloride has a very interesting set of properties. In hindsight, you can say it's rare on Mars because biology, it is very soluble in water, and once it's in water, microbes tend to break it down and turn it back into chloride. So as fast as you might form it up in the atmosphere or elsewhere, it gets turned back by life into chloride. The fact that you see so much perchlorate and so little chloride in our little sample on Mars might suggest to some that there hasn't been any life there for a long time. Of course, it might suggest to others that were there life there, it would have something to eat. So you can use this to interpret either way what the implications are for life on Mars. But let's focus back on our TECP discussion and brines. One of the properties of perchlorate is that it's very, very soluble in water. It's deliquescent. It will absorb water from the atmosphere, and it will keep water from freezing down to about minus 70 degrees, which turns out to be the typical frost point temperatures on Mars. About the time we discussed this, we discovered this, we published it, as you can see in the bottom right. At that point, the only time people ever heard about perchlorate was as a contaminant in our groundwater, and by coincidence, just about the same time, there was an article about the Jet Propulsion Laboratory remediation of its Superfund site and the fact that it was contaminated with perchlorate back home on Earth. No, we did not export it to Mars. We honestly found separate native perchlorate on Mars. So what does this tell us? Okay, well, it tells us various things. One subtlety has to do with bringing about a complete new look at the old Viking experiments we did back in the 70s, from which everybody concluded that there was no life today on the current surface of Mars. And not to say that experiment was wrong, but the conclusion was reached because nobody found organics on Mars with the mass spectrometer. And it turns out, now that we know perchlorate was present, we also know that had there been any organics, they would have been burned with the perchlorate to produce chloromethane and dichloromethane, which in fact were found. So they probably were contaminants. I don't think anyone would stand up, or very few people would stand up and say, we've changed our mind, we found organics in Viking after all, and therefore evidence of life. But it did tell us a great deal about what may be wrong with our strategy for looking for organics on Mars. Because when you put perchlorate in the mix and heat it up, it will burn. So that was important. This is probably the most complicated idea I'm going to show you in this whole discussion, which has to do with the balance of liquid and vapor and ice on Earth and on Mars. And what I've done is I've plotted the range of temperatures we experience on Earth, on the left, in various places. And you can see in the upper left, the boiling point of water is way, way, way higher than temperatures we normally experience. Normally 100 C, it can be a little bit lower if you have under high altitude conditions. The temperature range we experience may go up into the 40s centigrade, may go down in most places to no lower than minus 25 or so, except in really cold places. The dew points are similar to the temperatures, and the freezing points cover 0, a little lower for salty water. And the point is that under normal Earth conditions, you'll get vapor, you'll get dew, you'll get frost, you'll get ice, and Earth as a result is a very interesting planet, and the one thing you don't get is boiling. Mars, on the other hand, as we understood it, prior to these findings, it also has a broad range of temperatures, but the frost points are very, very low, which means that, and the freezing points, well, we assume they're near 0, but if there are extreme brines, they may be suppressed like on Earth. The boiling point is actually very close to 0, and you get temperatures up to the boiling point in the summertime near the equator, unlike Earth. But if you look at this picture, you'll say, okay, I'm never going to get liquid here because there's too big a gap between those frost points and the freezing and the melting points. Just too big a gap. All you'll ever get is ice. It'll never get humid enough to allow there to be liquid. So now that we think about perchlorate brines, which don't freeze until they get down to minus 70, that picture on the right looks a lot more like the picture on the left. In other words, if you think about perchlorate brines and other similar very strong brines that are liquid down to very low temperatures, you can get liquid and vapor and ice just as you do on Earth. It's an interesting concept. Do these brines exist? We don't know. Pictures like I showed you at the beginning with these water-like seasonal features start to suggest they do. The permittivity results for TECP start to suggest they do. And so maybe we have a different way of thinking about the phases of water on Mars as a result of combining the TECP and the chemistry measurements. And finally, in the words of William Blake, to see a world in a grain of sand. Okay? The first thing you do on Earth, if you were studying soil, I use the word loosely because soil on Mars doesn't contain all the organic matter that we usually think of when we say the word soil. The first thing we would normally do is look at it under a microscope. What are we looking at? What's there? Is it fine? Is it clay-like particles? Is it coarse? What colors are the particles? We did that on Mars for the first time, before and since. There's been no microscope that's gone to Mars with the resolution to see all of these little tiny particles the way we did on this instrument. And to do this, we had to have a little optical bench, put soil on the equivalent of a microscope slide, focus the microscope, whereas mostly what's done on Mars is the equivalent of what you would do with a hand lens or a magnifying glass. So we did this, and we saw a background of these bright orangey red rusty particles. Literally, they are iron oxide rusty particles that color everything. But when you look closely, you see they're a very, very tiny fraction of what's there. And almost all the mass are these beautiful, rounded, colored everything from brown to perfectly transparent little gemstones. We found when we moved around our substrates, our microscope slides, certain ones had magnets to hold the particles on, and we were able to isolate a group of these larger particles that look like Easter eggs. Again, all colors from clear to black, and these are little gemstones. That's the bulk of what the Martian particles look like. In the upper right, you can see a topograph taken with our atomic force microscope. These are things that are so small you can't see them with any optical microscope. But there are a few particles there that look like phyllosilicates, that look like clay. So it suggests that clay isn't entirely absent from the planet, and indeed, it's been found certain places on Mars from orbit. So finally, what do we do with all this data? Well, it turns out you can put together the size distribution of particles and compare it to size distributions from Earth and from the Moon. And there's theories about what the slopes of these distributions look like that I won't get into. I'll just get to the bottom line, that when you've done this and fit the slope, you find that the soil is very deficient in tiny clay-sized fine particles that on Earth are formed by water. As particles get smaller and smaller, you can't break them mechanically anymore. So the only way to make really fine particles is to etch them in water. The fact that we didn't find those particles, that the distribution told us these are all particles formed by breaking, not by chemical erosion, or maybe by polishing as they bounce around, tells us that there has been negligible history of exposure to water at this site. So we put all this together, and we have perchlorate suggesting brines. We have permittivity measurements suggesting you might get a little dampness from time to time, but we have size distribution saying maybe time to time, but not amounting to a whole heck of a lot. You start emerging with a picture of Mars that looks like a planet that is very dry, but where liquid is not entirely unknown, and appears in certain exotic places. Whether that liquid can support life if it's so briny, we don't know, but it gives us a lot of food for future thought and future explorations. So putting it all together, what have we learned? The polar regions on Mars are vaster than we previously thought. Water vapor is in equilibrium with the ice on the surface, and that's what controls how much there is. Perchlorate brines can be thermally stable at the ambient relative humidities on Mars, and they probably exist in small quantities at the Phoenix site and elsewhere. But the soil on Mars is abraded rock. Its primary is reworked pyroclastic material, and it doesn't have much evidence of exposure to water, if any at all. In other words, it's been very, very dry for a very long time. So I want to thank you for your attention. I want to thank my friends and colleagues at Decagon Devices for making this possible, and urge you again to think like scientists, work like farmers, and dream like children.